we're going to take the derivative of the cosine of the arc cotangent of x. And to start off, we're going to draw a right triangle to help us sort out the trigonometric functions on the right side of the equation. So keeping in mind that arc cotangent is a function that turns an adjacent side over an opposite side into an angle, which we're going to call theta. We'll put theta here. And cosine is a function that turns an angle, which is our theta in this case, into an adjacent side over hypotenuse. We can say that we have arc cotangent of x. So the x is the ratio of adjacent side over opposite side. So would it be convenient? One triangle we can use is to say adjacent equals x, opposite equals 1. So we have opposite side equals 1, adjacent side equals x. And then since we're solving for cosine, we're looking for adjacent side over hypotenuse. So we'll use the Pythagorean theorem to solve for the hypotenuse. So opposite squared plus adjacent squared equals hypotenuse squared. And we already have opposite, so we have 1 squared, which is just going to be equal to 1, plus we have the adjacent side squared, which is equal to x squared, and that equals the hypotenuse. So we have the square root of both sides, and we're left with hypotenuse equals the square root of 1 plus x squared. And the reason that we're taking the principal root and then we're not getting like a plus or minus the square root of 1 plus x squared is because we're actually dealing with vectors here. Whenever we draw a reference triangle, we're dealing with vectors. So we have the adjacent side in the I direction and the opposite side in the j direction. And then the hypotenuse is just the scalar distance between the origin and the addition of those two vectors. And it's a raw scalar distance, which means it's by definition positive. There's no such thing as a negative distance. So I'll have to think that. And I'll just rearrange this as x squared plus 1 because it has a better ring to it. So generally we're concerned when when a function which can go negative ends up in the hypotenuse. So everything in the hypotenuse of a Pythagorean triangle is going to have absolute values around it. And so in this case it works out because although x can be negative, negative x squared is always a positive. This function, the square root of x squared plus 1, will always be a positive. There's no value for x that's going to make this a negative. So we can forget about these absolute value symbols, and x squared the square root of x squared plus 1 is cool to use. So we can rewrite this. We can rewrite this equation as y equals cosine of theta, because we defined arc cotangent of x as being equal to theta, and then we can say that equals cotangent of theta equals adjacent side, which is x, over the square root of x squared plus 1. And then we can scroll down and let's take the derivative of both sides of that equation. So dy dx is equal to the derivative with respect to x of x. And actually we're going to write this, the denominator as a fractional exponent. So we'll write x times x squared plus 1 to the negative 1/2. Then from there, we can break this problem up further using the product rule. So we have x as the one function, and then this whole business over here as the other function. So dx is going to equal dx of x times x squared plus 1 to the negative 1/2 power plus, I'll fix that so it doesn't look like a t, plus x times the derivative of x squared plus 1 to the negative 1/2 power. Now we can work on taking these derivatives a bit. So dy dx is going to equal the derivative of x with respect to x is equal to 1 times, we have x squared plus 1 to the negative 1/2. And then we'll add to that x times, we'll have to use, looks like we have a function nested within a function. We have x squared plus 1 is the one function, and that's to the negative 1/2. So we have a nested function, which means we're going to look at using chain rule. So let's work that out over here, because it'll take a bit of space. So I'll draw an arrow, and then you can copy and paste that. And so, like we said, we'll use u equals x squared plus 1. And then we have the derivative with respect to, well, just use that same bit over here. We have the derivative with respect to x, but we'll replace x squared plus 1 with u. And we can replace d dx. It's the same. The derivative with respect to x is the same as du dx times d du, which is just chain rule. So du dx, let's take that first. Du dx is going to equal the derivative of x squared is going to equal 2x plus the derivative of 1 is equal to 0. So plus 0, which is just equal to 2x. So we can bring this down and say that's equal to 2x. And then we'll multiply 2x by the derivative of u to the negative 1/2 is going to be negative 1/2 times u to the negative 3/2, which is going to be equal to negative 1 over u, which is equal to negative 1 over u to the 3/2 times 2, excuse me, I forgot that it was to the 1/2. So we have negative 1/2 times u to the 3/2. And then we're going to undo the substitution. So u is equal to x squared plus 1. So all of that goes under all of that is x squared plus 1, all of that to the 3/2. Looks like when we multiply, these 2's are going to cancel out, so we can get rid of them right now. And then x times negative 1 is equal to negative x. And we have taken our derivative there. So let's go back to the main equation. So 1 times x squared plus 1, all of that to the negative 1/2 is just equal to x squared plus 1 to the negative 1/2, because the 1 coefficient doesn't change anything. X times negative x is going to equal negative x squared. We can bring these together closer. And let's bring it down a bit while we consider if there's anything else we want to do here. Okay, so I'll just rewrite this as 1 over the square root of x squared plus 1, and we are done. Actually, one more thing. Let's bring this negative from the negative x squared over here, because that looks nicer. And now we are done.